Calculus. My name is Curtis Brown, and I have Tom, Dick, and Steve Kokoska on the line with me. We're going to be talking about the difference quotient, looking at different modalities, ways to look at the difference quotient via tabular, graphical, or analytic, maybe some visible ways to kind of check out the difference quotient. We've got some tech tips lined up for you. So Tom's going to be doing some things on the TI-84 plus CE. Steve's got some great content, though, for us to get us kicked off. So Steve, take it away.
All right. Thank you very much, Curtis. Let's see if this works. How about that? Can you see that screen? Is that working tonight?
I see it.
Yes,
All right.
it's
Fantastic.
good.
So indeed, tonight we're going to talk about the difference quotient, and we are going to look at this in at least three different ways. We're going to look at it tabular, graphically, and even analytically. I still believe that that's a very important part of looking at the difference quotient, and that students should be able to solve some of these problems analytically. And we'll look at a couple. So let's take a look at this number one. As usual, I'm going to try to solve a problem or two, and then I'm going to hand it over to Tom. He'll show you some tech tips, and we'll go back and forth. And if you have any questions, please send them to Curtis. Please feel free to interrupt us. We enjoy the questions, the participation along the way. So, all right, let's start out with a function f given by this expression. It is a polynomial. It is a quadratic. And let's define this function m. And m of h is given by this expression, which indeed is a difference quotient. I'm just going to abbreviate a little bit off to the side to remind myself that is indeed a difference quotient. It is f of a plus h minus f of a divided by h, where a is equal to 3. So we're going to do several things with this, and ultimately, we want to know what happens with that expression as h gets smaller and smaller, as h gets close to 0. So the first thing we're going to do is find a specific value of this function m. We're going to find m of 2. I'm going to try to see what does that really mean and sketch a graph of what m of 2 is telling us. Try to illustrate this m of 2. Then we're going to look at a table of values for m of h for small values of h, or as h gets closer and closer to 0 from the left and from the right. And we're going to see what that table of values suggests about that limit. And then finally, we'll do something analytically. We'll use the limit laws, try to recall some of those limit laws, and to evaluate that limit analytically and explain the meaning of that value. What does that limit really mean? So here we go, down towards the bottom here. Let me see if this is working tonight. I'm going to arrow up a little bit. Let's take a look at m of 2. So all I'm going to do is to take that value of 2 and plug it into that function given for m, that expression given for m. So that's f of 3 plus 2, which would be f of 5 minus f of 3. How did I get these values? Well, I went back up to the function, the expression for the function, and plugged in. Did a little bit of arithmetic and a little bit of simplifying over here, and I ended up with a value of -1. So what does this really mean here? M of 2, remember, this difference quotient, represents the slope of the secant line through these 2 points. Where did they come from? Well, let's see. The starting value is 3. Where does 4 come from? Well, that's f of 3. F of 3 plus 2 was 5. And that's f of 5. So I don't know if you can see the colors on this, Curtis, but the blue curve, well, that's a graph of y equal f of x. I plotted the 2 points, 3, 4, and 5, 2, and I've drawn in this secant line. And m of 2 is simply the slope of that secant line. So that's cool. We're on our way here. Let's take a look at a table of values. See if I can arrow up a little bit here. Oh, come on. There we go. Ah, too much. Okay, so I've got a table over here with values of h, and all I've done is simply plug that into the function, plug each value of h into the function m, and evaluate it. And in true AP calculus form, I've given you 3 digits to the right of the decimal. So as h approaches 0 sort of from the right-hand side here, as it gets smaller and smaller, here are my values over here of m of h. And notice they seem to be getting closer to 1. And again, as h gets closer and closer to 0, but this time sort of from the left-hand side, the values of m once again, well, seem to be getting closer and closer to 1. So this is a tabular or numerical suggestion, way to look at this difference quotient. And it suggests that that limit, as h gets closer and closer to 0, is indeed 1. It's not a proof, but the table certainly suggests that. So now I'm going to try this analytically. I'm going to take a look at this limit as h goes to 0 of f of 3 plus h minus f of 3, all of that divided by h. Okay, so I'm going to take this 3 plus h and I'm going to plug it into the function. I'm just going to stop here for 1 second. I'm going to put parentheses around here if I can. I noticed in my class, I'm not sure if in yours, Tom, but I noticed in my Calc 1 class, one problem, one issue that many of my students have is simply evaluating a function at sort of odd or different arguments. How do you evaluate this function f at this argument 3 plus h? Well, sort of bluntly, every place you see an x, you have to put a 3 plus h, and then you do as much simplifying as you can. Then I'm going to subtract off f of 3, that's this expression. So let's see here if I've got this right. I expanded out this 3 plus h squared, multiplied the 7, distributed the 7. There's the minus 8. Simplified that numerical value. I think that's going to be a minus 4. Now, some good things happen here. I think it works out that all of these constants cancel out. I've got a plus 7h and a minus 6h, so there's plus 1h. There's a minus sign out in front there, so that's minus h squared. And some really good things happen here from this point. Both of those terms in the numerator have an h in them, so I'm going to factor 1h out. And now I'm able to cancel, and I'm left with this limit after all of that. I can evaluate that limit because that's just a polynomial in h that is continuous. So I can evaluate that function, evaluate that limit, excuse me, by direct substitution, and that's just 1. Beautiful. Just as an aside here, at my session in NCTM, I had a couple of questions about this, Curtis, so I just wanted to remind people about this. Look, if you have not evaluated this limit yet, then this limit symbol must follow all the way down until the limit is evaluated. I had a question about, well, you know, my students don't like to use equal signs. They like to use arrows. Well, okay. So I might not see equal signs here. I might see an arrow like this. Would we accept that on the AP Calculus exam? Well, probably. But my blunt answer to that is, let's use correct notation. Let's use the equal sign here where it's appropriate. So what happens if this limit sign appears just once and it's not there anymore? Well, that's a tough call. It depends upon the year. It depends upon who the chief reader is. But again, my blunt response to that is, you know what? Let's make sure that we're all using correct notation. Part of the CED, the revised CED, is notational fluency. Let's try to use correct notation. So finally, after all of that, what does that value really mean? What is that limit? Well, that is the slope of the tangent line to the graph of f at that 0.34. And I've tried to visualize that with a graph that I produced with Mathematica. I've got some TI-Nspire screenshots coming up a little later. But the graph of y equal f of x, remember, is the graph of a parabola. I think there was a minus sign out in front there in front of the x squared, so it opens down. And you know what? That looks pretty close here. I believe this visually. It looks like that line is indeed tangent to that curve at the 0.34. Okay, great. Tom, I'm sorry. I probably beat that one into the ground. I'll let you try a technology tip here.
Okay, no problem, Steve. Sounds great. All right, let me see if I can share my screen. So I'm hoping I've got my TI-84
Yes,
showing.
sir.
Looks good to me.
Fantastic. So, um, yeah, I'm old enough I can remember teaching for years calculus without any technology. And I know my students came away from these limits of difference quotients, like you just performed, Steve, as this kind of temporary torture. We would put them through until we showed them the shortcuts for taking derivatives and things like that.
Yeah,
But really, closer to the heart of what's going on is thinking about that difference quotient and what it represents. It's the slope of a sequent line, and you're taking a limit of those slopes to get the slope of the tangent line. And the tables of values are just fantastic numerical ways to see that. Those tables would be really tedious to make, even with a calculator, if you had to kind of hand punch in the calculation for each entry. So I
yeah,
just wanted to show how we can take advantage of the functionality on a calculator to build these tables really quite quickly and then really see what's going on with them. So it's basically, I'll be showing how to create a table like what Steve had, but very quickly on the 84. So
okay.
let's take a look at that. First thing I'm going to do is I'll go to y equals and get my function entered in. And I believe that was, let's see, negative x squared. And we've got plus 7x minus 8.
Right.
Okay, so we've got our function entered in y1. And I do realize there's a table feature on 84, but for our purposes, I'm going to suggest that the stat editor is a really nice place to do this. And I hope you'll see why. So I'm going to go to stat. So I press the stat key, hit enter. And now I've got something that looks kind of like a spreadsheet. These are the built-in list names, L1, L2, L3, L4. But I'm going to create a list of values. That's going to be my list of H values. So I'm going to go up to the header for L1 and actually hit the insert key. So second insert. And now I can name this list whatever I want. I'm going to name it H because this is my list of H values. And what's nice about this is, and I think Steve will be doing some more tables like this, this list of H values I'll be able to use over and over again because the limit we look at with difference quotients, if you set it up with H as a parameter, is you're always looking, what happens as H goes to 0, okay? So Steve chose a variety of values here. Let's see, I think he had 1 and -1. Whoops, excuse me. Oh, I know what I did. Sorry. I didn't go down to the entry. Oops. I'm fumbling here. Let's see. Let me go back to stat. Apologize for that. Okay, so
There you
H,
go.
that's where I wanted to be. I think I was still up in the header. So my apologies on that. Okay, so let's put in 1 and -1. And then I think, let's see, the next values were plus or minus 0.05. So 0.05, -0.05. And then, let's see, we've got, what's it, 0.01. Okay, so 0.01 and -0.01. So Steve was careful to have values that are coming in from both sides of 0. And then let's go to, tell you what, I'm going to go ahead and jump to 0.001 and -0.001. So this won't be the entire list of values, but I just want to illustrate kind of how this would look, okay? So I've got a list of H values here. And now I'm going to go over to list L1. I'll go up to the header, and I'm going to define my difference quotient in L1. Now remember, we've got our function in Y1. So what I'm going to do is build a difference quotient here. So let me pull up y1. I go to my y variables, there's function y1. And I think we were evaluating at 3
Right.
plus h. And then we're taking a difference between that and just plain old y1 of 3. And then we're dividing that entire difference by h. Now, what's h here? Well, h is actually a list of values. So what's going to happen in L1 is it's going to take each value of h, plug it into this, compute the result, and put that as the corresponding entry beside that value of h in L1. So it's very slick. Let's hit enter, cross our fingers, and uh-oh, what did I do here? Division.
Uh-oh, where's the division by 0?
I didn't, did I?
Hey,
I might have not hit enter or something. Let me look.
no, Tom.
Yes.
You got to use the list name, not the variable h. You got to use the list named h. So
Now,
I have to pull
Curtis,
that from second list.
okay. So Curtis, you know I did that on purpose just to illustrate that.
You know, I thought maybe you were doing that on purpose just to see if I was paying attention and
So
not
wait a minute,
distracted by the chat.
Wait a minute, Tom, don't you have to go up a little bit here? Wait a minute, you were in the first row?
And
So two things here.
yeah, I think
Underneath
you're
of
right.
edit,
Here we go. Get up to
header.
L1. Yep.
Yeah.
Thanks. Okay,
And
so
now
let's
you
try
can-
that again.
And I'm really curious, Tom. Mark made the mention about snagging the y variable from sec alpha trace, alpha F4, rather than going through vars and y vars. It's a little
Right.
faster.
Okay. Yeah, so let's go ahead and illustrate that on my next call up of y1.
Sure. But
Yeah.
right now you're trying to get that list h, right?
Right. And so to do that, I'm going to do alpha h again.
No, you're
But
not.
we need to
No,
the list thing goes in front of it.
no.
Yeah, arrow back to the h and
Okay.
put in second and list. There you go.
There it is.
Now I'll pull number 7 there.
There you go.
Ah, so
There we go.
this
Now
thing.
delete off that other h.
There we go. All right.
There we go. Now we got it.
That's the list h. And now we can, now let's do that shortcut for getting y1. So again, that's alpha of trace. And there we see we've got our various y1 and y0. So I'll fill up y1, evaluate it at just 3. And then we'll close off that difference. And then we'll divide by, and again, we're going to divide by the values in the H list. So I want to make sure I refer to that list. So let me do second list. There's number 7. There we go. And let's see what happens now. Fingers crossed again. Bingo.
There you go.
Looks fantastic. Okay. All right. So as you can see, if you don't make the mistakes I did, this could go fairly quickly. So, but it really is, I think what's nice about this is actually set up for you to investigate difference quotients in terms of age for lots of different things. You've already, it would just be redefining L1, or if you wanted to look at more than one, you could define L2 and L3 in similar ways for other functions. So this is a very kind of nice way to look at that. And frankly, I think this is more suggestive than trying to use the table feature, because the table feature, you would end up kind of having to use X as your variable, where like we're using H. H is the thing that's varying in each of these computations. So here it's much more suggestive that we're using H values there.
So
All
Tom,
right. Yes, go ahead, Steve.
so what happens what happens if I want to try this with a different function y1? If I go back and change y1, I don't think this is dynamic, is it? Does L1 change automatically?
Um, well,
So
let's see.
what do
Yeah,
you need, Steve?
So that L1 is defined in terms of this function y1.
Oh, so the way he could do that
Yes.
is to lock the formula for L1. So he defined L1 in, or sorry, yeah, he defined L1 in terms of that list H
Y1.
and
Yeah,
Y1.
right.
Uh, and that worked great for the first calculation. But then if he arrows back up and sees list one, it's actually just going to be the list of those values. But
Correct.
you can store or lock an expressions like a formula, if you will, in there. And I can show you how that
Well,
might.
I'm just curious if
But
if you do that and now you
mhm.
change Y1, does L1 change dynamically?
It would, yes, but you have
Okay.
to do something. You have to put quotations around where Tom put in the y1 of 3 minus h, and
Okay.
you would have to uh, put quotation around that.
Okay.
I would make, um, and I could see instances for doing that for sure. Um, I would maintain though, Steve, that you wouldn't do that often for difference quotients because just as likely you're not only going to change your y1,
Right.
you're also likely to change your target value. At what point are you doing a difference
Sure.
quotient?
It's not going to be
That's another
3. Yeah.
change that would require you to
Mhm.
change that formula. But
Yep.
you're just changing that one formula for L1, and then you've already done all the work for entering the values of H. That's
Mhm.
one and none. Yeah.
Okay.
Um, so yeah, it's not dynamic unless you do this thing that Curtis did. But because there's more than one thing you're probably going to change and edit, I'm not sure locking it is something you'd want to do too very often, unless
Gotcha.
you're always looking at the same point.
Gotcha.
All right. Well,
Okay.
I will stop the share and turn it back over to you, Steve.
All righty. Very good. Okay. Let's see if we can take a look at problem number 2. So here's an interesting function f, defined, it's a quotient. Holy Toledo, it's got an exponential function in it. It's got a trig function and it's got a log function in it. Kind of typical of a calculator active question on the AP exam, one that would be probably impossible to integrate, and I don't want to take the derivative of this. So let's see, we want to use a table of values to see if we can approximate f prime of 1. And then we want to use the difference quotient, and I confess this is something that Tom taught me a while ago. I want to see if I can use the difference quotient to sketch a graph of f and f prime on the same coordinate axes. And then, often when we're teaching, at least when I'm teaching difference quotients to begin with, I'm asking my students to see if they get an expression for f prime, can they explain the relationship between these two graphs, f and f prime? Because that sort of sets me up for what's to follow, what's to come here. All right, so let's see if we can estimate f prime of 1. So the first thing we're going to do is take a look at this difference quotient right here. It's f of 1 plus h minus f of 1 divided by h. And we're going to take a look at that value for values of h that get closer and closer to 0, similar to what we did, in problem number 1. Well, here we go. H is getting closer and closer to 0 from the right-hand side. Here, H is getting closer and closer to 0 from the left-hand side. And I feel kind of lucky here. This expression m of h seems to be approaching the same value. It kind of looks like to me, with 3 digits of accuracy, that it's getting closer and closer to 1.067. Sometimes when I do these problems and I arrive at this numerical value, I think, well, maybe that's a numerical approximation of an exact value that I might be able to see here. But boy, looking at that expression for f, I'm not sure. Could you take the derivative of that? Yeah, I guess I could. It's a quotient, so that would be the overriding rule. But then there's a product in the numerator. So, oh boy, and there's some chain rules in there. I don't think I really want to do that one. So it sure looks like f prime of 1 is close to 1.067 as we approach this with the numerical method. So let's take a look at part B, and I've got a couple of screenshots here from the TI-Nspire. So the very first thing I did here was I defined this function f of x. I hope you can see that on the screen. And then I defined a difference quotient function here to be f of x plus 0.01 minus f of x divided by 0.01. So what I did was I took a specific small value of h. Why? Well, because as h gets closer and closer to 0, we expect this difference quotient to get closer and closer to that value, f prime of 1. So, in the grand scheme of things, this function m should be returning values very close to the derivative of f at x. This is really just a cool way to discover what some derivatives might look like. So, all right, on the right-hand side, I've graphed this function f and the function m, this sort of difference quotient function, if I can call it that. I don't know if you can see it on the screen or at least down here. My f is in blue, and I think my function m is in green. This is pretty cool. There's a good graph of this function f, which I wouldn't have guessed that. There's some funny stuff it seems like going on in here with this function. Sort of wobbles a little bit in there. I wonder why. And then there's a graph of an approximation to the derivative of f. Okay, I did the same sort of thing down here in this graph with Mathematica to get a little bit bigger, a little bit better maybe picture, more accurate. And what do you notice? What do I hope my students notice at this point in the class? Well, it sure seems like when the function f is increasing, the difference quotient function or the derivative is positive. And it sure seems like when it's decreasing, the difference quotient function or the derivative, the approximation to the derivative, is negative. That's a great way here to lead into, well, chapters 2 and 3 and beyond here. And what does f prime tell you about the graph of f? I like that one. Tom, should I continue with 3 or do you want to do something else here?
Yeah, I might do a little bit more here, Steve, if that's okay with you.
All righty. There you go.
Okay. I think this is just an occasion to kind of share, just go over making that table of values again, and also illustrating, plotting that difference quotient function like we did. So
very good. Yeah.
Let me go to share my 84 screen again. And see, I think I've got it up. Check it out. Okay, so takes a little while to enter. I went ahead and went to y equals, and you can see there for y2, I've gone ahead and entered that same function that Steve had. So it's e to the negative x over 20 times the sine of x over 2. And it's a long enough expression. I'm going to go here to see the whole thing. All divided by the ln of that quadratic there. So there's that very complicated function. Let me turn off the y1 from the previous problem. And we might just do a quick graph here. See if it looks like the function Steve had. Yeah. Okay, a little bit different window, but it looks pretty good.
Indeed it does. Very good.
So let me go back to stat again and go to the editor. And there's those H values again.
Mm-hmm.
I think Steve had a couple more additional values in there. Actually, he had more than what I had here, but he also had a couple that were closer to zero. So I think it was 0.0001 and negative 0.0001. And I will point out that notice that the list L1 here didn't update. This is what Curtis was talking about is, once it was produced, it is now just a list of numbers and it's not dynamic in any way. And that's okay because we've changed functions. So I'm going to go up and redefine L1. Let's clear out the current definition. Notice that L1, I should have spoke up, but you saw L1 didn't have the formula in there anymore. It just had that list of values. Okay, so we're going to build another difference quotient. This one is centered around 1, right? So our thing, let me take the shortcut here, alpha trace. Y2 is our function now. And I needed to get a parenthesis in front of that. Let's see. All right, let's try that again now. There we go, Y2. And it's Y2 of 1 plus, and this is where we need to pull the list H. So I'll go to the list menu. There's number 7 is H. And then we'll subtract just Y2 of 1. And then we're going to take that difference and divide it by our list of H values. So again, I'll pull the list H from the list menu here. There we go. And hit enter. Boom. And there we go. So there's those values produced very quickly. And we can see, I noticed that I don't know if you mentioned this, Steve, but you had a couple of more values in this table than you did for the previous example.
Yes.
And I'm guessing the reason for that was you had a little bit of difference in that 4th digit over here, and you were looking for it to converge enough that you'd be confident that you had an answer correct at 3 decimal places. And that's a good strategy. I mean, you could come up with some really pathological functions that might not work for, but that's a real good rule of thumb there. So fantastic. And then just to show how do you do a difference quotient function? Well, for a function as complicated as Y2, this is really nice that we can just define it by referring to the label Y2. So I'm just going to make a difference quotient function here. And that's going to be...
Hey, Tom.
Yes, sir.
Is there a reason you wouldn't want to use the fraction template there to make it kind of look like the difference quotient would in my textbook?
We could do that. I was cognizant of those sometimes with tracing values and stuff coming up with
Oh, they might look like fractions. Well, it won't in this case because
of the exponential and all those.
You got an exponential in there, and you got some stuff there's no way it's going to be nice, pretty fractional numbers. So
yeah, let's go ahead and do that though. So that's the fraction template. It's the alpha shift of the xt theta key there. So gives us a vertical fraction like that. And now we can put the difference in the top, which will be Y2.
And Steve, while Tom's inputting this difference quotient here,
yes,
I did get a question in the chat.
Oh, good.
That we had a student, I think, that said that they would like to see another example similar to this one, which I think you have. Maybe we could take a quick look at that, because I think maybe there'd be clear up a couple of things for them.
Okay.
Looking for another example similar. Yeah,
Okay, so we'll ask when Tom is finished with this one.
sure.
We'll do another example, but with a simpler function.
Yeah, that sounds good.
Okay.
So here's that difference quotient, and now the variable x is we're going to be doing a difference quotient with a very small h value, 0.001, but this is for each x value. And so we get lots of different difference quotient values, and we're going to plot that as a function. Let's go ahead and graph it and see what happens.
How about that?
And it graphs a little bit slower than the original function. And the reason is it's calling up y2. Y2 itself is a pretty complicated function, but it has to evaluate it twice in that difference. And so it's doing, roughly, I could say about 3 times the number of calculations that the original function was doing. And the original function was already complicated. But we get a very nice looking graph where you can do that analysis like Steve was saying, is that where my original function, the red one, is decreasing, the black function's values are negative. And where the values are increasing, the difference quotient values are positive. So it's kind of classic derivative function behavior analysis that we value the derivative so much for. Okay, I'll
so
stop.
Tom,
Yeah.
we're gonna try another one on the fly here. Okay.
Sounds great.
So let's go back to the y = menu.
Sure.
And if you'd be kind enough to turn off y2 and y3. And in y4, let's just use a simple function. Let's just put in the sine of x. So this is kind of pretty standard. This is pretty standard, Curtis, in class. So we begin to look at the derivatives of trig functions, and we'll start with the sine of x. How do you discover what the derivative of the sine of x might be? Well, one sort of classic way to do this is to sort of draw a graph of the sine of x and take a look at specific values, points on this curve, and sketch in the tangent line and try to guess what is the slope of that tangent line. And then plot those points on a separate graph. For this value of x, the slope is this. For this value of x, the slope is that. And then connect the dots. That's kind of one way to discover this. Another classic way to do this is analytically, is to go back to, well, the strict difference quotient and look at this analytically. And that's very painful because it involves 2 difficult limits. So let's suppose we want to discover this in the way that we've been talking about this tonight with this difference quotient function. Let's suppose we want to determine, well, what is the derivative of the sine of x? What does it look like? So instead of just starting out with a table, Tom, let's go directly to this difference quotient function. So let's put in a fraction here, and let's do y4 of x plus.
And you know what, Steve, for this function, I think I'll go ahead and put in the actual sine function, if that's
okay. Sure, that would be good.
All right, so we've got the sine of x plus like 0.001.
Right.
Oops.
Well, that'll work too, but that's all right. That's good.
Oh, did you have a different suggestion on that?
No, that's fine. That's great.
And then just minus sine of x.
Right.
And divide by our difference of
Yep.
our x values, which is just the 0.001.
So why again, Curtis, should this work? Because that expression is an approximation to the derivative of the sine at each value of x. So if this function sine is, what was your phrase, Tom, is pretty well behaved,
Mm-hmm.
this should give us a pretty good idea about what this derivative looks like. So we're going to get a graph. The pink graph will be the graph of sine. There it is. And here comes an approximation to its derivative. And that's really cool.
Mhm.
Because you can look at that and say, wow, that really looks like the cosine of x. That's a great way to discover what this derivative is. And now, given that numerical, given that visualization, I can go back and
what you were talking about, Steve, at first was just starting with the pink graph and just
yeah,
eyeballing it. You could say, okay, at 0, it looks like my sine curve has about a slope of 1. That means my derivative value, we should plot for x equals 0, a value of 1.
yep.
Okay, over here, somewhere around 1.5, it looks like, or maybe pi over 2. Okay, we see a very flat graph, which means the slope is about 0. That means the point we should plot on our derivative function should be 0. And so you could plot a few points, just kind of eyeballing, well, approximately what you'd be plotting slope values for
Right.
each x value. And that's a good way to just visualize. And what this difference quotient thing has really done is a very fine job of approximating that derivative for every point across the screen there.
Yep.
Or I should, every pixel is what I should say there. So we get a really nice, and this, what you picked as an example, Steve, is one of my favorites.
I like this, yeah.
It's just to do this difference quotient and look at that green graph and say, does that look familiar to you at all?
Yeah.
It's like, wow, if I didn't know better, that sure looks like a cosine graph. And then, of
And
course,
so
analytically, we can prove that then.
And so this is another nice way. I believe this would work, Tom. We could go back and simply change y4 and graph this again. We could discover the power rule this way. We could
Right,
discover
for
all
sure.
sorts of derivatives this way, right?
So again,
Yep.
here, and you were suggesting this, Steve. If I was going to change y4 like over and over again and do lots and lots of difference quotients, I would want to make my y5 actually y4 of
Right.
x.01 minus y4 of x. That way, whenever I updated my y4,
Yep.
y5 would update automatically. Yeah.
And
This difference quotient was so simple. I just want to make sure people realize this was exactly what we're doing when we do that difference quotient.
And if you would, before you leave this, Tom, do one more thing for me. Would you go to the window key up in the top left there?
Sure.
And on the x min and x max, just for the heck of it, make these something like minus 2 pi to plus 2 pi by pi over 2. Just to demonstrate that we can indeed do this, we can make x scale a multiple of pi, and we might be able to see this a little bit better.
Okay. You know, another option, and certainly Tom's going to put this in there using the what you guided him to do, but you can also use the zoom trig,
yeah,
and get that
quicker,
get that scale pretty nicely. He said pi over 4 or pi over
2 is fine. Sure. Now graph that one more time.
Okay. All right.
Yeah, that's fine, Tom. That's great.
Okay. Let's
zoom 7. Mark's got it memorized.
Yeah, that's the trig window, which may be pretty close to this.
I think it's pretty close to that. I don't remember what zoom trig actually does.
I'm not sure what the x scale is on it. Okay, so let's graph.
So there's the sine, and here comes the cosine, and you can see a little bit more clearly this idea of, well, where the sine has a slope of 0, the derivative goes.
I mean, it hits it perfect. It really does. That's beautiful.
It's really
pretty
nice.
close. Yeah,
makes me smile every time.
And I mean, you actually referred to it as cosine, Steve, when it's actually a difference quotient.
Yes.
I'm just curious if we go down to y6 and put in the actual cosine.
Oh, that's a great idea. Yeah.
What's that look like? Can we even detect the difference between?
You may see a pixel difference. I don't know.
Maybe the 0.001 maybe is just small enough that it might be hard to see. Let's check a look. And
Oh, look at that.
It's just right on
That's
top.
pretty good.
That's
Right on
because of the
top.
resolution of this screen. It really isn't different.
Perfect.
That's pretty
Great.
good.
Very
Great.
nice.
This is just a great way, I think, to have students discover things, discover concepts like this. And I think, Tom, you and I and Curtis, we really believe that if a student discovers this and sees this, they really learn it better somehow. And learning by discovery, it becomes ingrained in them. So good way to
That's the
do it.
truth.
Good way to do it.
To own it whenever it's that way. Yep.
Yeah, yeah. Take ownership in it. True, Curtis. Yeah. Yep.
And while I wouldn't, label what we just did in any way, shape, or form as a proof that the
Right.
derivative is cosine, I have found this kind of illustration is actually more compelling and convincing than the analytic proof is pretty complicated and
Yes, it is.
pulling out some kind of some geometry
Yep.
things that students aren't necessarily very comfortable with.
Yeah.
While this is like, yeah, I believe it. This is like
Yeah.
cosine behaves like the derivative of sine. Yeah.
Yeah.
All right. Well, I'll
Very
stop
good.
the share there and turn it back over to you, Steve.
Okay. Thanks, Tom. All right, let's see if that's still working. How about that? All right, I'm actually going to take a look, Curtis, now at a couple of problems analytically, and I still believe that these are good problems to do. We are talking about notational fluency, and there's some great, I think, problem-solving skills in here, skills that should not be lost on our students. They should still know how to do some of these things. I remember my calculus teacher telling me, once you do all of these and you understand what's going on in the background, now we can approach these with a little bit easier method or a different method by learning some differentiation rules. Well, all right, let's take a look at this expression right here. The limit as h goes to 0 of f of x plus h minus f of x divided by h, the limit of this difference quotient. And let's see what we can find that limit for each of these functions. I won't go through every single step here, Curtis, but I think in each one of these problems, there is a different sort of problem-solving technique that is important for us. So the first one is 2 divided by x minus 1. So here's the expression I want to evaluate. In this first step, I'm simply going to evaluate f at x plus h, evaluate f at x divided by h, and see what I need to do here. And again, I'll remark that this is often where my students make a mistake right there in this first step. How do you evaluate this function f at this argument x plus h? So let's make sure we get that right. What do you do here? Well, I'm actually going to do two steps in one. I'm going to get a common denominator in the numerator, and I know that sounds kind of weird, but I'm going to get a common denominator in the numerator, and I'm going to multiply by the reciprocal in the denominator, so there's that 1 over h. So without getting into the weeds here, without doing all of the details, I multiplied everything out in the numerator and got this expression. And thankfully, a lot of good things happen here. The 2x's cancel, the 2's cancel, and I'm left with a minus 2h up here in the numerator. That's a really good thing. I have h as part of a product in the numerator, and it's part of a product in the denominator, so I can cancel it. I'm left with this expression. Now I can use direct substitution because when I plug in h equal to 0, I do not get a 0 in the denominator. I do not get 0 over 0. I do not get an indeterminate form. Remember, in this limit expression, we're treating h as the variable. And so x is considered a constant here in that expression. And so when I do that, I think I got a minus 2 divided by x minus 1 quantity squared. Neat problem. Let's take a look at this one. The second one, f of x plus h minus f of x divided by h. Well, again, the first step here, I'm just going to evaluate f at that expression, at that argument x plus h, subtract off f of x over here, and I'm going to do the same sort of thing that I did in part A. I'm going to get a common denominator in the numerator. I'm going to multiply by the reciprocal of the denominator. And boy, it looks awfully complicated, but there is some value to doing this by hand. I'm going to multiply out everything in the numerator, and I'm going to do some canceling. And I think I'm left with this expression here in the numerator. Fortunately, once again, I can factor out an h out of each one of those terms. And I'm going to be able to cancel that with the h as part of the product in the denominator. And now I've got an expression here where I will be able to evaluate this limit. And you know, the truth is that I am really skipping a step here. I'm taking the limit of a quotient. And because each of these limits exist and is non-zero, I can write this as the limit of the numerator divided by the limit of the denominator. We go a little bit further. We can say, well, we have a quotient function, and we have a quotient, and it's continuous at 0, so I can just plug in h equals 0 and evaluate this. After all of that, correct me if I'm wrong here, Curtis, I think I've got a minus x squared minus 4 divided by x squared minus 4 quantity squared. And boy, I really wanted to simplify that a little bit, but I don't think I can. If I factor out a minus 1 out of each term in the numerator, darn it, I don't think I can cancel anything. So that's my limit. How about that? And one more that involves a square root. This one's got a couple problem-solving techniques in it, I think. So as usual here, I'm going to evaluate the function at x plus h. And here in this step, what I'm going to do is rationalize the numerator. And how do you do that? You multiply by 1 in a convenient form, and the expression that I use in both the numerator and the denominator is the conjugate. Why is that a good idea? Well, because then the numerator becomes the difference of squares. It looks kind of funny, but it's the difference of squares. So in the numerator, I'm just going to have 2 times the quantity x plus h minus 1 minus the quantity 2x minus 1. And I'm not going to do any multiplying out here in the denominator. We'll leave it like that. And if I've done everything correct here, is this right? I'm going to have a 2x and a minus 2x there, so those will cancel. I've got a minus 1 here and a minus minus and a plus 1, so those will cancel. And so in the numerator, I'll be left with just a 2h. H is part of a product up there in the numerator, part of a product in the denominator. That's nice. I'll be able to cancel those. Now I'll be able to evaluate this limit as h goes to 0 by direct substitution. And if I've done everything correct, I have a 2 up here in the numerator. And let's see, if h is 0, son of a gun, both of those expressions underneath the radical will be the same. So there's 2 of them. The 2's will cancel. And here's my final value, my limit, 1 divided by the square root of 2x minus 1. So as I do all of this, as I solve lots of these problems, I'm learning some problem-solving skills, and I'm learning a lot about pattern recognition here that I'm going to store for solving later problems. Let's take a look at this one, which is a little bit different.
Hey.
I apologize, Tom. Is there a calculator tip in here?
No, not really, other than exploring it numerically like we've done before. But Steve, I would have a request that
Okay.
if you don't mind, you always have a great problem set that has more than we can ever possibly.
Sure.
I wonder if you wouldn't mind kind of jumping to number 6, because I
Sure.
think that's just a really nice kind of AP type of tabular question that
Okay.
gets at this difference quotient in context. So
All right. And we'll
if you don't
finish
mind.
off with 6 tonight. That's a great
Okay.
idea. Okay.
That's a really good idea. Thanks, Tom, for jumping us up there.
All right, so we're going to take a look at
Or
6
down
if
there.
I can get this correct. Here we go. Well, there's my table. All right, so this table shows the number of electric cars in thousands that were sold in the United States from 2011 to 2023. And actually, this is pretty close. I looked this one up. So this is actually pretty darn close. So indeed, Tom, this is very similar to a lot of AP FRQ questions. So find the average rate of change from 2016 to 2020, and we want to look at the units of measure. And we want to sort of interpret this value, if we can, in the context of the problem. And then in B, we want to estimate the instantaneous rate of change in 2017 and think about the units of measure. Well, okay. How do we solve part A? Well, if we want the average rate of change, this is really nothing more than, well, son of a gun, a difference quotient. It would be C of 2020 minus C of 2016 divided by 2020 minus 2016. In order to get those values in the numerator, I've got to go to the table. And did I do that right? 2020, we've got 294. 2016, I've got 160. So I did that subtraction. And let's see, in the denominator, I've got a 4. And I think after a little bit of simplification, I get 33.5. The units here, let's see, is that correct? It would be thousands of cars sold, yeah, per year. How about that? So I think those are the units. So how do I interpret this? Well, the average number of cars sold in thousands from 2016 to 2020 is 33.5 per year. How about that? Let's take a look at B. I'm going to try to arrow up here a little bit if I can. Mark Corrali is still trying to help me figure out a good way to do this. Mark, if you're listening, I think it works better if your fingers are dry. How do you like that? So consider the following estimates. Now, this is an interesting question because it doesn't tell you in this part B, it doesn't say what interval to use. Now, those of you who follow the free response questions carefully will notice that over the last couple of years in problems like this, where a student is asked to estimate this instantaneous rate of change, it often says using a particular interval. So it might say using the interval 2017 to 2018, or it might say using the interval 2016 to 2018. This one doesn't say. So it's not clear which interval is the best to use. So I did 3 separate intervals, and then I'm going to give you another suggestion perhaps for using a fourth one. So the first thing I did was I fixed my 2017 and I went a little bit to the right. So I went C of 2018 minus C of 2017 divided by, well, all right, that difference is 1. And I got a 166. So that would be an estimate of the instantaneous rate of change at 2017. If you think about this graphically, what have I done? Well, I've just kind of drawn the secant line, and I've got a slope of a secant line, which we think in the grand scheme should be close to the slope of the tangent line. Well, what if we went in the other direction? The slope of the secant line between 2017 and 2016 is 34. Wow, there's a big difference there. So there, an estimate for the instantaneous rate of change is 34 thousands of cars per year. Well, what if we went a little bit to the right and a little bit to the left? What if we took a look at the secant line between T, was it equal to 2016 and 2018? Well, now this time, we've got an estimate of 100. 3 very different estimates of what F prime is equal to. How do we know which is best? Or is there a better one? That's a good question. That's a good challenge question. Here's another way we might get an estimate of the instantaneous rate of change of 2017. Many texts suggest this. Go 1 to the right, go 1 to the left. So get an estimate, get that slope of the secant line going 1 to the right, so that 166. Get that estimate going 1 to the left, 34. And then take the arithmetic mean of those 2 values. There's another estimate, another way to estimate what F prime of 2000, or C prime, excuse me, of 2017 would be.
But is it really a different one, Steve?
Oh, that's a good question. Is it?
I'm noting that the average of your 166 and your 34 is exactly 100.
How about that? So, an open question, Curtis, is, and we'll leave it with this tonight. An open question is, how do we know? Is there any way to know which of these estimates is sort of the quote unquote best? Great. A lot of fun, Curtis.
That was a good one.
And I
That was
didn't
a lot
get
of
the
good
chance to
content
ask
tonight.
you any questions, and you didn't sing tonight, Curtis.
I
So
didn't sing. I spared everyone that terrible sound that might come through of me trying to sing tonight. Really appreciate that. That was good content, Tom. Thank you for taking the time on the calculator, and thank you both for jumping in and answering questions as people had them and asked them. Teachers, I put my email in the chat box there if you want to go back and look for it. Curtis@ti.com. Send me an email and I will respond with a link to the professional development hour certificate. And otherwise, I look forward to seeing everyone here in about 2 weeks. We've got another session. We'll be chatting it up about, I forgot what the content is in 2 weeks here. I don't remember. You guys remember off the top of your head?
I'll tell you in a second. It is differentiability and its consequences.
Differentiability. All right, we're going to be chatting about differentiability here in a couple of weeks.
Curtis, you will also post the solutions.
I
And
will post the solutions
new
in
problems
the
will be
morning.
ready also. New problems will be
And I
ready.
will also post the new problems as well. So
Very good.
we'll make sure that everything is out there. Thanks again, everyone in the chat. Thanks for the good conversations and questions. We'll see you in a couple of weeks.
Great. Thanks, Curtis.
All right.
Very cool.
Very, very good. Very